Section 11.2 is going to discuss a chi-square test for association. So before I get into that too much, here's a little data table that talks about whether or not a subject lied and the results of a polygraph test. Naively, when I was young, I thought, why do we even have trials? Just give them a lie detector test. But a lie detector test is good about maybe 70% of the time or so. So it's not really as convincing of an evidence as we might like. What's our threshold for being convincing? Does anyone know? Anyone want to guess? There's 5% or 1%? Yeah. So 99% confidence level, 95% confidence level, 5% significance level. So we're going to test whether or not these two variables are independent. Now those two variables are part of what's called a contingency table. Now I haven't given you this handout. It is available online, but parts of it are on the back of your one of your handouts, I think. In any case, you'll hear this kind of analysis being applied to contingency tables or cross tables, etc. But what you're doing is you're going to try and decide whether or not your column variables and your row variables are independent. So it's a test of independence. Now, it's not the same kind of rigid independence that you would expect from a probability course. This is going to be statistical independence. So we have to prove pretty much that one row is dependent on the other or there's an association. Now, a lot of the work that we're going to do here is going to be done for you behind the scenes, but it is going to fall down to one of these kind of calculations. Observed minus expected squared divided by expected. Now, how you exactly get those things isn't really going to be part of our course. I can show you if you're interested, but most of this is going to be pretty much the same as usual, except all our null hypotheses are going to be the row and columns are independent. Now, I want some actual things here pertaining to your problem. I don't want just this generic stuff. But the rest of it, find a p-value, input your data, fail, reject, or reject H0. When it comes down to the very bottom, you have to state your conclusion in words. And I'm trying to draw your attention to something here in number 6, step 6. What is it you think I'm trying to draw your attention to?
There's an association.
Okay, what else am I trying to scream out in words here? Step. Yeah, you can't prove causation with these kind of tests. It's tempting. It's going to be very tempting to say, oh, one causes the other, but that's not the kind of conclusion we can get when we're doing a chi-square test for association. The most we can conclude is that there is an association. By the way, what are some of the things that can prove a causation? Does anyone list a couple of them? Silence. Wasn't it just like a week ago that we talked about proving causation? Replication of studies, dose response.
Replication of studies, dose response, removing confounding variables. Sorry. Have a plausible
causal. Yeah. A casual relationship. We want to establish a casual relationship. I think there's a website for that. It's called Tinder. In any case, all right, before I get in trouble, let me go on here. So we want to establish a causal relationship. That's going to require more work than what we're going to do here, which is going to establish an association. Now, the way this is going to be set up, we're going to assume that these two variables are independent, run a hypothesis test on that, and then based on a p-value, we're going to accept or reject, and then state our conclusion in words. Now, your conclusion in words is going to be a little bit more challenging here because there's something missing from our null hypothesis. And that is, we don't have an equal sign here, do we? So that nice little guide that we have to wording your hypothesis conclusion, can't really use it in this section. Sorry. Not that I'll forbid it on the test, it's just it doesn't really apply here as easily. Okay, so let's start out with example A here. Your null hypothesis. is always going to be that these two variables are independent. Now give me something more descriptive than the row and column are independent. I will not take kindly to that on an exam. So whether or not the subject lied, bless you, and the results of a polygraph test are independent. What does it mean for two variables to be independent? Can anyone reach back to your work on probability? Yeah, one influences the other one. If they're independent, then the outcome of one variable is not going to have any influence on the outcome of the other variable. They just behave independently. One does not affect the other. Now, the alternative, you could say that there's a dependency. I prefer to say that there's an association. The alternative is that there is an association between the results of a polygraph test and whether or not a subject lied. All right, so there's your null and alternative hypothesis. Like I said, a little bit different. Not quite the same as what we're used to, but that's what we're stuck with. What comes next? So that's our first step. What's our next step? Alpha. And in this case, alpha is 0.05. Yeah, 0.5. A 0.5 value for alpha would not be very good. And let's find our data. Now I've got your data for you on a link that you can find on D2L. So hopefully you got that open and StatDisk open. Let's go grab that data, section 11.2, jump down to example A, your polygraph test, and let's copy those. Let's clear out the old stuff. I strongly suggest you clear out the old stuff each time you input new data, because sometimes there can be like a space character or a tab character that won't show up, but then all of a sudden you'll get this error from StatDisk that says, oh, your columns aren't of equal length, or something else annoying like that, and it's really kind of a bummer. So we got our data input, we're doing good there. So input the data. What's step 4? You need to find a p-value. Where do you think I'm going to go in StatDisk to try and find a p-value? Analysis, good. And what type of analysis we're going to do? Ah, well done. Somebody was paying attention. Contingency tables. Yeah. Sam, did you get that one too?
No, it's Cosmo.
Oh, okay. Good job. Good job. Now, it's kind of nice because, the analysis is really not going to require much. It's just going to check off the two columns that represent our data and evaluate. Bam. So, Cosmo, what am I looking for here? P-value. Nice. 0.0002. Joy, what's that going to mean our decision is? What are we going to do with H0? Got this for our p-value. What should we do with H0? Reject. Good. This is smaller than our value for alpha, so we're going to reject H0. Now here, we're going to have to wing it a little bit. Our little wording the hypothesis conclusion doesn't really help us out too much because we don't have a nice parameter that we're testing, mu equals something or rho equals something. It's just worded like this. So there's a couple possibilities. Ultimately, we're concluding this. One possibility is you could say that the data reject this is true. The other possibility is that the data support this is true. So either way you want to say it. So you could say there's sufficient data to reject the hypothesis that whether or not the subject lied and the results of a polygraph test are independent. That'd be fine. Or you could say the data support the conclusion that there's an association between the results of a polygraph test and whether or not the subject lied. Either one is fine. There's going to be some flexibility in what you choose here. I think I'm going to choose the latter of these. So there is sufficient evidence to support the claim that there is an association between whether or not a subject lied and the results of a polygraph test. Okay, so there's an association. That's nice. Is it a perfect association? No. If you actually looked at the data, and let's take a look back at the data. I'll give you a second to finish copying this down. Which cells are the correct cells? Just holler out some numbers. Which cells have the correct decisions? 37 and 34. If it said they lied and they did lie, that's a correct decision. If it said they didn't lie and they didn't lie, again, another correct decision. So 52 and 52. So you've got 104 different subjects in this test, and of those, 71 of them were correctly categorized. So 71 out of 104. That's about 68%. I don't know. Somebody can check me on that. So it's not perfect, but all we're concluding is that there's an association. Maybe there's a tendency for people to be diagnosed correctly. Okay, great. Is it perfect? No. But there is that tendency, and that's as far as we can conclude on this one. Comments or thoughts on example A? That one? Sure. Did you just want to copy something down, or? Okay. Let's take a look at example B. I confess, I'm not exactly sure that all the information was copied down in the statement of the problem because it feels a little vague. We'll go through it anyways. The big thing that I wanted to look at in example B is going through the motions of our hypothesis test. The table below summarizes data from a survey of men and women using 1% significance level and assuming that the sample sizes of 800 men and 800 women are predetermined, tests the claim that the proportion of agree-disagree responses are the same for subjects interviewed by men and subjects interviewed by women. Does it appear that gender of the interviewer affected the responses of women? All right, that's kind of like a follow-up here. Right now, what we want to look for, is there an association, or are these two variables independent? So let's move on down to example B. One of my students in my morning class was talking about a professor from outside of the Royal Oak campus, we'll say, and kind of saying that they did a lot of the calculations by hand, like including your regression stuff. So we're avoiding a lot of that stuff, but one thing I ask for in return is stuff like your H0 and your conclusion, your HA. They be written in terms that reflect the problem. Don't give me something that's generic and can be written for just anything. So in this case, gender of the interviewer, and agree / disagree are independent. The alternative hypothesis, you could say that there's a dependency. Again, I prefer that there's an association between those two. There is an association between agree / disagree and the gender of the interviewer. Yay. All right, so it does get a little bit lengthy, tedious, wordy, etc. Sorry, not much that we can do about that. What's our level of alpha for this one? 0.01. Good. So let's reach out and grab our data. Again, there's a Google Sheets link that has this data. So I'll go down to example B and grab that. When you put it into StatDisk, clear out your old data, paste in the new data. You can go to analysis, contingency tables, and that looks pretty good so far. Do want to change this to the 1% significance level, and I need another column to evaluate. There we go. P-value 0.000. All right, so input the data, check. Say again?
What are we gonna do?
All right, so our p-value is 0.0000. And Oz, you seem to be really ready with this answer. So what's going to happen with our null hypothesis?
Reject.
Yeah, reject H0. Your p-value is less than alpha, so you're going to reject H0. Pretty simple. Do you want to collect some of our own data? Maybe we'll do a hypothesis test of our own data? Yes, no?
Yes.
Okay, good. I'm going to send around something you can just add on to the data from my morning class. We're going to find out if there's an association between whether or not you're wearing a jacket or sweater and if you like Coke or Pepsi. All right? So here we go. Let's find out. So as I pass this around, just put a check in the right box. And then we'll do the analysis in a little bit. It's a great question. So if we can let me answer Cosmo's question, folks. If we can, I can answer Cosmo's question. He says, does the size of the p-value accept whether we accept or reject? Yes and no. I mean, if it's a really, really small p-value, you can feel pretty comfortable in rejecting. Because what that p-value says is, what's the chance we can get the data we got or something more extreme against the null hypothesis? And that probability, if it's really small, makes you think that, well, either we got some unusual data and we got a small p-value because of it, or the null hypothesis is false. So you have those two choices. Generally what we decide is when our p-value is less than alpha, we're going to reject the null hypothesis. We're going to say, you know what? It's unlikely that the null hypothesis could be true given our data. So the smaller that p-value is, the more confident you feel in rejecting that. Now, we're going to see a really, really interesting p-value for the next one. And I'll be kind of curious to see what you guys have to say about some of our discussion afterwards. As far as this one is concerned, you could say a couple different things. One of them, you could say the data support this. I kind of did that with the last one. So let me just say that there's sufficient evidence to reject this claim that they're independent. Just to mix it up a little bit. On a test, you could say either one. There is sufficient evidence to reject the claim that the gender of the interviewer and agree/disagree are independent. And like I said, you could also state it that the data support the claim that there's an association between gender of the interviewer and agree/disagree. So there's a couple ways you can word that. I think you've seen both of them here at this point. Are we okay with the conclusion there? Lizzie? Lizzie, you got a sweater. Just check. Are you not sure to check Pepsi or Coke?
I got it.
All right, she's got this. All right, she's got this. That's good. While that's going around, let's look down at this next one, which is actually a true story. Kristen Gilbert was a nurse that worked in the Veterans of Medical Affairs Center in Northampton, Massachusetts. So nurses around her were noticing that there was a lot of people who died at times when she was working. And they collected some data. And that data was later used in the grand jury trial of Kristen Gilbert. Now the grand jury trial, is everyone familiar with the grand jury trial? What does that do? Grand jury trial just says there's enough evidence to move on to an actual formal prosecution. It doesn't convict or not convict somebody at that point. You're just saying, well, we need to look into this further. So this is the data that they collected, that they had shifts when she was working, shifts when she wasn't working, shifts with a death, shifts without a death. And take a look at this. There's more deaths when she was working, the 217 shifts when she was working, as opposed to 1,350 shifts when she wasn't working. That looks pretty bad. That looks really bad. And now this evidence, like I said, was used in the grand jury trial. So let's move on then. Let's do our hypothesis test of these two. And then I'm going to have a follow-up question that I want you to discuss. So example C. Let's see. H naught. So how do I want to state this? Deaths on a shift and whether or not Gilbert was working are independent. Bless you. what's the alternative hypothesis going to be? Yeah. There is an association between deaths on a shift and whether or not Gilbert was working. No, this is actually a true story, and I'll tell you a little bit more about it after we talk about it and get our conclusion here. So it's actually a pretty sad story, to be honest. Now, because we're talking about somebody's guilt or innocence, you want to be really, really careful about this. So we're going to choose alpha as 0.01. We want a high burden of proof if we're going to proceed on this. Step 3, we're going to input our data. And then step 4, we're going to get a p-value. We'll reflect on that p-value, especially in light of Cosmo's comments. So example C, grab this data here, paste it into StatDisk. Analysis. Contingency tables. Let's make that a 1%. And wow. So another p-value of 0. Well, it is. It is. But you gotta let me get there. Nicole?
For all the examples in 11.4, we're just going to reject over any.
Well, I don't know. We got some data that we're collecting right now, aren't we?
Okay. Yeah, sorry.
All right. We'll find out. We'll find out. So let's see here. So we get a p-value of 0. Cosmo, reject or fail to reject? Reject. Now, do we feel pretty confident in rejecting this? Yeah, you got a p-value of 0. But a p-value of 0 doesn't really describe just how far out there unlikely this is if the null hypothesis is true. So to appreciate that, let's look at the actual plot of the data. Now, in order to get into the rejection region, in order for your test statistic to be far enough to the right that it's you're going to have a p-value of less than 1%, you need a test statistic of 6.63. Take a look at our test statistic. It was 86. And if you want a graphic representation of that, then take a look at the plot. The rejection region starts to the right of that red line. Look where our data is. It's like way out there. I mean, you need an electron microscope to see how small that p-value is. I mean, it's just minuscule. It's really tiny. So you can feel really comfortable in rejecting the null hypothesis here. It's just unlikely to be true. So reject H0 is our conclusion. And now here's my challenge to you. Reject H0. Let's see. Let's say you write the conclusion together, and I'm going to have a little follow-up for you. Let's see. There is sufficient evidence to reject the claim that deaths on a shift and whether Gilbert was working so we're rejecting the claim that those are independent. Are independent. The data just screams out that that's not true. Now what I want you to decide, I'll give you a couple minutes to think this over and talk it over with your friends. And please just talk about this problem, not talk about the Lions or Thanksgiving plans or something like that, but please talk about this problem. Can this evidence be used to convict Kristen Gilbert in a trial, in the actual trial? Talk about it amongst yourselves first, and then I'll solicit questions. Cosmo, did you have something other than your conclusion?
Grand jury trial or actual?
No, actual trial.
Okay.
So this data was used in the grand jury trial, but could it be used in the actual trial to prove that she convicted or that she killed all these people, or at least some of these people?
In the real world, any person would use that as essentially kind of and it wouldn't
You don't know why?
no.
Do you know now?
More no. You know, yeah, like in a real
Trying to get it
and
Somebody's going to change. No, but I don't think you're going to be like, no, wait a minute. So what's the conclusion?
Yes.
Can you use it or not?
No.
Yes. Yes?
No.
It may not work. You remind me of a funny thing that people say about data. All right. So I've got a variety of opinions. I didn't get over here. What do you guys think over here? Can they use this to convict her, to help convict her? I got a no, a couple no's. Nicholas, you disagree. We actually have a law professional over here. Alex, what's your prognostication on this one?
So you can't use it in any way to convict, but you can use it to lay a foundation of leading to suspicion.
Okay.
What cause?
So you can use it to lay a foundation, but you can't use it to convict. And that, I guess I can go with that. The one thing I want to remind you of, that this handout, and you can get a copy of this on D2L, and I'll also put it in the notes, is the part that I was screaming out here. You can't prove causation with this.
I said that. You literally walked over everything that I just said and said.
I didn't. No.
There's a literal law.
You're gaslighting me. I didn't respond because I wanted other people to think about it. That's not exactly what was true.
Gaslighting your favorite word right now? Because
It is. It is. All right.
Whatever. I said,
All right.
Never speaking again.
Promises. All right. All right. In any case, no, you can't use it to prove that she's guilty. What if there was another nurse working at the same time on those shifts? Maybe she could have done it, right? Okay. What if?
An old person nurse, and she only works with old people.
Yeah.
Of course, they're gonna die. They're old.
Yeah. I mean, it's like, so there's what are, if you remember, on the back of your handout is a reminder of something. There are confounding variables in statistics. These are variables that affect both the cause and the response, the cause and the relation, cause and effect. Maybe Maybe she was working in the same shift that somebody else did that did cause the murders. Maybe she's hygienically challenged and she smelled so bad it killed these people, but she didn't really overtly kill these people. I mean, we don't know. So you can use this to, as Alex says, maybe lay a foundation, but you can't use it to convict. This kind of data cannot establish causation. It only establishes association. Now, the sad story is that this was actually true. I think what she was doing was that she was grabbing epinephrine and injecting patients, giving them a heart failure, and then heroically trying to rescue them and impress her boyfriend. Now, unfortunately, not only was she bad at rescuing them, apparently, but I think a lot of these people were people that couldn't communicate, couldn't talk. And so it's just really tragic. She's serving life sentence someplace in the Northeast, deservedly so. So, yeah, no, it's actually a true sad story. All right. Let's take a look at our data here. Our Pepsi, Coke data.
You had us kind of confused.
So, is there association between whether you like Pepsi and Coke and whether or not you're wearing a jacket or sweater?
No, it's cold outside.
Yeah.
It's cold outside.
Well, first of all, not too many people like Coke who aren't wearing a sweater, so maybe there is an association. I don't know. I don't expect one. I don't see any reason there would be an association. Now, if we're not going to get an association, what kind of p-value would you expect? Below or above 0.05? Above. You're going to fail to reject. That's what we expect. You know, if we have enough observations to do this test, then I would expect that you're going to have a rather high p-value, closer to 1 than closer to 0.05. So let's put this data in, take a look. So let me clear out this data. And we had 16 in the first cell, 10 in the next cell. 24. It's a lot of Coke drinkers who are wearing jackets today, and only 4 here. So let's run the analysis and find out contingency tables 1 and 2. We can do this at a 5% level because if we get it wrong, it's not really life-threatening. And whoa! Now this is a little different than my morning class. My morning class, there was an association. So you guys, there's some association between whether or not you like Pepsi and Coke.
Not just because Coke is better.
Yeah. There's a lot of people who are definitely more in favor of Coke. But yeah, there is an association. So I'm sorry, I fully expected that there wasn't going to be an association. You're not always going to get an association, though. All right.
Which one is
Okay. Let's finish it up. We got one more example here to do. Come on. Remember, our goal is to get out early. 2 minutes is way early for me. I'm worried that you're going to berate me on Rate My Professors. Like, yeah, he kept on letting us out 2 minutes early.
You have a habit of letting us out late.
And we don't charge you any extra for that extra. Yeah, it's free of charge. It's just my commitment to you. All right, let's see. Let's find example D here. No, that's the wrong one. Here we go. So I think I've got this whole data set here. This is, again, a true story. It happened at the University of California, Berkeley. An administrator noticed that it seems like a lot more men are getting accepted to UCal Berkeley than women. And they went into a panic, like, uh-oh. So naturally, who do they call to rescue? The math department. They're like, hey, look into this. And they did. And even though these numbers look pretty bad on the surface, well, what they did is they dug into this further. Now, I could not find the names of the departments that were involved. So the article I read just called them Departments A and Department C. But here's what was going on. If you look at it, there was a lot more men applying to Department A. Take a look at the acceptance rates for Department A. They're pretty good, aren't they? 62%, 82%. In fact, women are getting accepted at a really, really high rate here. But how about Department C? Are your chances pretty good of getting in Department C? No. Not as good. But take a look. The number of women applying to Department A is pretty small. That's where it's like almost a sure thing. Whereas a lot more women apply to Department C, where it's tougher to get in. And so overall, when you combine these results, this is the effect that you're seeing. So what you're seeing is the results of a confounding variable. And those results kind of skew the overall picture. If you didn't split this up, then you'd probably think, all right, we got a problem here with gender bias. Now, I'm not saying that gender bias doesn't exist or anything like that. It does. But in this case, we can explain it this way. Now, Nicole, I somehow feel obligated to give you an example that doesn't work. My guess is that if you looked at acceptance and gender in this case, I don't think there's going to be any significance here. I think we're going to have a high p-value, but let's find out. Let's find out. So, let's see. Example D. No. Examples. Here we go. Yeah, this is the table that I want. So I want the values that are in black here, not the ones that are in red. Let's paste that into StatDisk. And run the analysis. Contingency tables. You better not prove me wrong. I'll be mad at you. There we go. P-value, 0.38. Nicole, what's that say we're going to conclude about the relationship between being accepted and not being accepted and gender for Department C? Yeah, you're going to fail to reject. They're independent, right? There's no reason to conclude that, one gender is favored over another. They're about the same, okay? So, yes, nicely done. Nice. So, beware of confounding variables. There are things that can muddle the relationship between a cause and effect. That's one of the things I asked you to know coming out of our lecture on proving causation. Anything else there on this one? Feeling okay with that conclusion? Okay, let's put this one in the books.